Cariad Eccleston's a computer science graduate of Salford University. After 15 years in the industry, she's now a freelance DevOps engineer working with local startups and businesses, and she builds awesome stuff. She's going to be talking about reading and publishing on the web when your internet is hostile to LGBTQ plus content.
Thank you very much. LGBT resources on the web are essential. They are essential to our health, our well-being, and sometimes to our safety. But these resources aren't always reachable. Sometimes we can't read them without risking danger to ourselves. And sometimes these resources aren't what they seem to be. We're going to talk about that. But first, hello, my name is Cariad Eccleston. This is my little intro because I wasn't sure if I was going to get one. I am a computer science graduate from Salford University, which is up north, but everyone's been simply smashing to me down in Devon since I moved down here. Probably, yeah, about 15 years ago, actually. And yeah, for 15 years, I've been building software professionally. And this time last year, I was a DevOps team lead for a global tax and accounting platform. And now I am a freelance engineer, and I work with local businesses. I've done some really cool with local startups, and we build awesome stuff together. It's not just me, and it's a lot of fun. And yeah, so I'm going to talk about LGBT content on the internet and being able to read it safely. But the first question I want to address is a question that I've been asked is about why is LGBT content on the web so important? Why why do we need to be special? Why do we need to isolate ourselves, as some people might phrase it? Well, there are some aspects of our lives that do set us apart online. For example, health issues, not just physical health, but mental health and sexual health. It's okay to prefer advice that's been given to you by someone who understands you, but that advice isn't always available in our local physical communities. We have specific legal needs because we have specific legal concerns, like discrimination of same-sex relationships or gender identity. We also buy goods and services online. We're not all blessed with the confidence just to walk into our local pharmacy and slap condoms on the table. And for some of us, it's just not safe to do that in our local communities. And safe sex shouldn't be reserved for people that only live in accepting communities. And speaking of communities, we have social needs. Let's not dismiss the value of friendships and of belonging somewhere and social support. It's human nature. And of course, it's not just LGBT people that use these resources. Our friends and our families and our employers want to understand us and they want to support us. So whoever reads this content online, it really does benefit us. So this information that I just talked about is widely available on the internet, thanks to a little military network built a few decades ago that was intended to survive wars. It became the internet. And while the architecture of the internet really helps to ensure that tactical data can flow between military installations, it doesn't really do anything to protect you from people that want to do you harm. I'm going to take a look at some examples of this harm and look at how we can protect ourselves. But just in case everyone here isn't a computer science graduate, we're going to look really briefly at how the internet works, and so we can understand where the problems are. So let's say you have a phone or a laptop or a desktop. It has an IP address, an internet protocol address. And everything on the network needs to have a unique address so that it can send and receive data. You also have some kind of interface to the internet. So this could be 5G, it could be a physical cable. In this case, we're going to go for a Wi-Fi router. We have a worldwide network of wires and satellites and routers that shunt data around, and they look at the IP address that the data is addressed to, and then they make sure they try to get it to the right place if they can. We have domain name system servers, and these convert domain names like prismexter.com to the IP addresses that are needed for addressing data. When you register a domain name, you're essentially paying to have it put into one of these big databases. And finally, we have servers that host websites, chat, and blogs and apps. And in the case of this example here, if someone was to ask the DNS server, where is prismexter.com, the address they would get back is 71.22.22.22. So if, for example, you're using your phone and you wanted to connect to PRISM Exeter, first of all, your phone would connect to the local network. And remember, you can only connect to things when you know their IP address. So for us to figure out what the IP address is of prismexeter.com, we need to ask the DNS server. And in this case, the DNS server will tell us the address. And then we have everything that we need to know, and we can make a connection to that server, and we can start downloading the content. So this is great. This works clearly, but we have to trust in a lot of moving parts. And there are 3 particular ways I'm going to talk about where this trust can be abused. The first kind of way that trust can be abused is an abuse of anonymity. We assume we have it, but we don't. Every time we make a connection to a website, our IP address and the server's IP address, they need to be visible in the data stream so that the internet's infrastructure can get it to where it needs to be. But because it's visible, that means it's really trivial for anyone with access to this hardware to record what domain names you're looking up and what your IP address and which IP address is that you're connecting to. And your IP address isn't random. It's assigned to you by your ISP. So if authorities wanted to find you, but all they knew was your IP address because you've been looking at something that they think you shouldn't be looking at, then that's enough. They can figure out who the ISP is based on that IP address, and then your ISP can identify you and hand over your contact details, your home address, whatever authorities ask for. And let's try to forget the idea that only criminals need to worry about being tracked. So let's say, for example, you're on a trip to the USA and you're staying in a hotel. Less than half of US states have laws that protect you from discrimination in public accommodations based on sexual orientation and gender identity. So could a hotel manager have their Wi-Fi router alert them if it detects their patrons connecting to an LGBT resource? Absolutely. Could they kick you out for it? They absolutely could. Granted, it's unlikely, but they could, and the law would not protect you. The next kind of abuse we're going to talk about is blocking. So according to research conducted by the Radical Librarians Collective, 98% of UK public libraries subscribe to curated categories of websites, like, in quotes, LGBT interest, and they use those categories to block access. So is a suicide hotline a health service? I think we'd probably all agree, yes, it is. But what about a hotline that's intended for suicidal LGBT youth? Is that still a health service, or is that LGBT interest now? Who decides, and what prejudices do they hold? We don't know. So blocking isn't just an irritation. It's not just about Netflix blocking Europeans from the US library. It's blocking deployed in good faith can prevent people getting the help that they need. Blocking is essentially a decision about the kinds of people who deserve, in quotes, help. And it causes harm. It really does. So the third and final kind of abuse is kind of insidious, and it's redirection. That happens when perhaps I detect that you're trying to visit prismexeter.com, but I make you visit my own server instead. One of the biggest and maybe misunderstood examples of this is the so-called Great Firewall of China. A lot of people assume that if you're in China and you search for something like Tiananmen Square or Tibet, that result's going to get blocked and maybe you're going to get arrested. What actually happens is that Chinese network infrastructure detects that you're trying to visit websites about these topics and just redirects you to alternative websites that present different facts, perhaps downplay historical events, and might even put doubt in your mind as to whether they actually happened. And since they're doing that, they don't need to arrest you because you can just disseminate this information yourself. So yeah, and you don't need to be as powerful as China to perform this kind of redirection. Any piece of network infrastructure could decide to redirect you or could be told to redirect you. Even your own internet router at home. There are no global laws that demand that internet routing is honest. So, I mean, that's kind of a downer. So let's rephrase these problems in terms of demands. What do we want? We want to be able to reach services that authorities don't want us to. We want to be able to communicate anonymously, by which I mean without sharing our IP address. You can block cookies and trackers all you want, but your IP address will still identify you. And finally, we want to have confidence that we really are talking to the services that we think we are. LGBT folks aren't the only people who find these qualities appealing. The US Naval Research Lab's been thinking about this kind of weakness in routing since the 1990s, because militaries and governments and probably spy agencies are also making the same demands that we are. Now, one of the reasons why the internet took off the way it did was because the protocols were published and open, and anyone could build in it and join in. When the Naval Lab started building out new protocols to fix these problems, they knew that they had to be published because they had to get buy-in and to get people using them. So they did publish them, and you can actually start using this stuff now. The protocols that they published were called onion routing. I'm going to talk about a specific open source implementation called Tor, which stands for the onion router. And yeah, so let's have another look at an internet diagram, but what it looks like with onion routing in play. So yeah, with onion routing in play, you still have a phone or a laptop or whatever you want to use, and there are still websites that you want to connect to that host apps or blogs or websites or whatever. And then all around us, all around the world are Tor relays. And these are just regular computers and servers. They are operated by unpaid volunteers, and they run the free open source Tor software. Whoops. With onion routing, your laptop never connects directly to the website like it would have done before. It chooses 3 relays at random, and then it asks them to pass the connection along. And this is called a circuit because it's a closed loop for messages going back and forth. Each one of these relays could be in a completely different country. So you could be in Saudi Arabia connecting to a relay in Scotland, then one in Oregon in the US, and then off to New Zealand before ending up at Stonewall's website in the UK. And your local network only sees you talking to an anonymous relay. Your local network has no idea what's happening on the other end of the circuit. So if you're in China, then the Great Firewall of China can't stop you connecting to a website you want, because it can't stop, say, a server in New Zealand talking to a server in the UK. Each relay only knows about the connection that's going in and the connection that's going out. None of them ever know the full path. So if the authorities ever confiscated any one of these nodes, none of them would hold information about you and the server. So it might know who you are, but it could never tell where you were going. Or it might know that someone visited this website, but it wouldn't know that it was you. But, you know, we're talking about trust again. What's stopping these relays from just reading the messages going back and forth? Couldn't they just spy on you as easily as anything else? The short answer is no. Before a message gets sent through one particular relay, your laptop has already negotiated encryption with the next relay. So only encrypted messages ever get sent through each one. But then here's the big question. How can your laptop negotiate an encryption key with something that's out there on the internet if there's a really good chance that someone's watching you? Let's go for a really, really simple example here. So what do we mean by an encryption key? Well, one really basic example of encryption is alphabet substitution. So if I wanted to send the word Stonewall to you and my encryption key was 1, then I could say I'm just going to shift the alphabet by 1. So S becomes T and T becomes U, so on and so on. So if I sent 2 box from to you, then you wouldn't know, well, people who are watching us wouldn't know what that means. The problem is, though, you also wouldn't know what that means, because I haven't told you yet that the encryption key is 1. How can we negotiate an encryption key of 1 if people are listening? If I just tell you 1, someone's going to hear it. This is a really interesting problem. I think it's really, really interesting. And it's solved by a little thing called DiffieHellman Key Exchange. If you came here for the cats that were promised to you, then this is the bit. There is a little bit of maths, but I think it's really interesting, and I think it's good to know so that you can have faith in what's happening in the network. So, DiffieHellman Key Exchange. Here's a quick example. So here we have Amy and Brooklyn, and they want to send encrypted messages to each other. And down here we've got Charlie, who's a very naughty cat who won't give them any privacy at all. So Amy and Brooklyn want to negotiate an encryption key while knowing that Charlie is watching. Now, Brooklyn likes to take charge. So Brooklyn decides that the basis of their encryption is going to be base 5 mod 23. Base is just a number that they're going to multiply, and mod or modulus is like division, but you care about the amount that's left over after a nice round division. So 10 mod 3 is 1, because 10 divided by 3, well, you get 3 each, but then there's 1 left over. The main thing here is that everybody, including Charlie, the spy in the middle, can see the basis of this mathematics. So first of all, Amy on the left rolls a dice and generates a random number. And Amy never ever tells anyone what this number is. All she does is plug that number into the maths. So we take the base, which is 5. We raise it to the power of 9, which is the random number that she picked. We divide it by 23. And when we do that, we get 11 left over after the division. And that 11, Amy can share that with Brooklyn. And we don't care if anyone sees that 11. We really don't. Makes no difference. In the meantime, Brooklyn's done the same thing. Brooklyn also rolls a dice. And for the sake of this example, we're not going to know what dice roll she got. All we know is that she does the same maths. So she takes the agreed base 5, raises it to the power of the random number, divides it by 23. She gets 10 left over. So then she shares that 10. So everyone knows the basis of the maths. Everyone knows that Amy calculated for her half an 11, and then Brooklyn calculated for her half a 10. Now we do the second and final round of calculations. Amy takes Brooklyn's 10, and that becomes a new base. So we're not multiplying, we're not raising 5, sorry, we're raising 10 now. She raises 10 to the power of 9, divides it by 23, and she has 20 left over. Brooklyn takes Amy's 11, that's the new base, so raises 11 to the power of her random number, divides it by 23, and then gets 20 left over. And this isn't a coincidence, they both got 20 left over because that's the power of maths. So now they can do alphabet substitution to share secret numbers, and Charlie in the middle has got no idea. Charlie, based on the information that got shared, Charlie couldn't possibly work out that the shared encryption key that they negotiated was 20. Right, that's the end of the maths. So let's see how that gets used for secure encrypted communication. Here's another internet diagram. So over on the left, you've got your laptop. Over on the right, we've got, say, Stonewall's website that you want to connect to. In the middle, we have 3 completely randomly picked Tor relays. We still need the DNS server because we still need to convert domain names to IP addresses. And over on left is the danger zone. So this is the local network that you don't trust. So it's got your Wi-Fi connection. It might even be your country's infrastructure that you don't trust. And our goal is to have a laptop in an untrusted network be able to connect to the website over on the right without anybody in the red circle knowing what we're doing. So the first thing we're going to do is, just like Amy and Brooklyn, we're going to negotiate a shared encryption key with this relay. I forgot to mention that when your laptop randomly picks these relays also describe the basis of their mathematics, so the base and the mod, that kind of thing. So we can, just like Amy and Brooklyn, we can negotiate an encryption key with this first relay. And our hostile network does know that we talked to this relay. But because this is a relay picked from thousands on the internet, they have no reason to, well, for the sake of this conversation, they have no reason to block us. They're not going to redirect us. This is just an innocuous, non-LGBT related connection. So now that we've negotiated that, we want to negotiate an encryption key with the next relay as well. Now, we could just connect to that second relay the way that we just did, but then our hostile network would see someone else that we're connecting to, and then they would see someone else that we're connecting to. And we don't want to reveal anything about the path that we're connecting. Actually, we want our laptop to be the only thing in the world that knows the exact path that we're taking. So what we do is we use the encrypted connection we've got to the relay and tunnel through to it to create a second encrypted connection. And then you probably guess we can use that encrypted connection to go to the third relay. And this gives you a clue as to why it's called onion routing. It's like an ogre, it's got layers. We have encryptions inside encryption inside encryption. And then now we've got a tunnel that goes way out onto the internet, and we can use that to talk to basically any website we want. And our hostile network thinks that we're only talking to one relay, and they can't tell what we're doing with that relay. So when it comes to us wanting to actually talk to a website, we can, we can construct a message. It's called a cell in Tor's jargon. And before we send it out through this tunnel, we're going to encrypt it. We're going to encrypt it so that only our relays can read it. So we're going to encrypt it for the final relay first, for the middle relay, and for the first relay. And as that message gets sent down the chain, each relay peels away a layer of encryption until finally the third relay decrypts the message, and it can see what the message is, and it can see that we want it to get this website. So the relay does a DNS lookup, and anyone who's watching the internet here, anyone who's trying to work out who's connecting to this website, the IP address that's visible at this point is the relay's IP address and not ours. We are private at this point, we're secure. And then it connects to the website, and if anyone's looking at the website's logs, they're only going to see that relay's IP address and never ours. And yeah, so no one can guess what we're doing. When the third relay has finished getting all the content that we want, it constructs another cell that contains all the information, and it sends it back down the chain. And when things go back down the chain, they get encrypted by each relay as it goes down. And each relay can't see the content. Like in this diagram, we can see inside the content, but remember, each relay can only decrypt the layer that is its color. Our laptop is the only thing in the world that holds all three keys. So our laptop is the only thing in the world that can peel away all three layers to get to the content. This is pretty good. We just successfully visited a website without revealing our IP address to our local hostile network. And anyone watching our network activity has no idea what website we just visited, and they have no idea what content we just downloaded. This is pretty good. Our anonymity has been preserved. But that's really only half the problem. Like, sure, we were protected, the reader was protected, but the publisher or the host of that information wasn't protected. So the server's IP address still needs to be known, because we need to be able to look it up. Otherwise, by the laws of the internet, we can't connect to it if we don't have that address. But if we can look up a publisher's IP address, then anyone can. Law enforcement can. And if you're hosting LGBT content in a country that criminalizes LGBT content, then, like we talked about before, it's really effortless for the law to compel your ISP to identify you. So is there a way that we can use Tor to protect publishers as well as readers? Is there a way that two parties can connect without ever knowing or each other's IP address, or without each other ever having to reveal their IP address to anyone? On the plain old internet, this is just not possible. But with Tor, we have a little thing called Tor Hidden Services, also known as the dark web, which I'm sure you've all heard of. But we're going to go over how it works, just in case you don't know. So here's the same pattern we had up before. So we have a laptop at the bottom left, which is us. We have a server in the middle that we want to connect to, and we're surrounded by a cloud of Tor relays. And the laptop and the server need to connect without ever telling each other what their actual IP address is. When the hidden service on a server is ready to start receiving visitors, it creates three circuits to random relays around the world. And these are called introduction points. Now, rather than choose a domain name for the hidden service, the service generates a .onion address or an onion key. You can't really choose what this is because it's a long kind of cryptographic string that uniquely identifies that service. And when the service has generated that key, it wants to publish it in directories, distributed directories all around the network. And it does that by creating circuits out of these directories and then letting them know, this is my ID, and these are the introduction points where you can find me. And note that it publicizes the introduction points, never ever its own IP address. Right, so let's say now we're on our laptop and we want to connect to Stonewall's hidden service. By the way, Stonewall, I don't think have a hidden service. It was just a nice, easy name to think of. So we need to create connections, create circuits out into the network so that we can discover any introduction points for the service we're interested in. And in this case, let's say we pick 82.22.22 out of the collection. So now we know the introduction point. Now we're not going to just connect to that introduction point and start demanding content, because we don't want to trust, if we can, we don't want to trust publicized IP addresses. Some bad actor could have looked up this same list of IP addresses, and they might realize that they have control of the internet infrastructure around this particular IP address, or they can do a takedown of that IP address, or they can do any kind of weird stuff with that particular IP address. So we don't want to trust 82.22.22 if we can. But we need to talk to the service somehow. So we're gonna tackle this by creating two circuits of our own. The first one we're going to create is a rendezvous point, and we will use this later if the service agrees to talk to us. And then the second circuit will just be used to let the hidden service know, if you want to talk to us, this is where we can meet. This is the halfway point. And if the service agrees that it does want to talk to us, it creates another circuit and it joins the dots, and now we have a connection. We have a connection that we control half of it, the service controls half of it, and we never ever shared our IP addresses. And people watching this won't know our IP addresses. In fact, remember that each one of these circuits is adding more and more encryption. So we are both entirely anonymous to each other. The publisher is protected as well as the reader, which is nice. So with all that said, let's have another look at our demands. Does Tor meet our demands? Does Tor allow us to reach services that authorities don't want us to? Yes. It doesn't matter if the library you're using is blocking the Trevor project, if there's a relay in Sweden that's doing that accessing for you. Does Tor allow us to communicate anonymously? Absolutely. Of the 3 relays that you would use in a regular circuit, only the first one ever knows who you are. And the domain lookup and the website request, they never ever reveal that IP address, well, because the other relays honestly don't know what your address is anyway. And finally, does Tor give us the confidence that we need, that we really are talking to the services that we think we are? Well, with Tor hidden services, yeah. The onion key that we talked about is cryptographically linked to the service. Plus the encryption and the obfuscation of the network just makes it nearly impossible to hijack, nearly. So remember, most internet protocols ask us to trust that humans won't be evil. Even VPN providers, they might promise not to log you, and they might promise not to share your details, but it's just a promise. It's up to you how much you trust them. We certainly couldn't stop them from doing these things if they chose to. Tor, yes, is still at the mercy of human error in a lot of ways, but for the most part, you really just need to trust the maths, and I'm okay with that. Anyway, that's it. This is me. I appreciate your time. Thank you very much. Yeah, my name's Cariad. I'm on Twitter at Cariad Eccleston. Like I mentioned, I'm a freelance DevOps engineer. If anyone wants to talk about that, then you can get all my details off cariad.me. Thank you so much for your time. I appreciate it.